All right. Hey, everybody. So today we are doing topics 25 and 26, both of which are logistic regression. But I mentioned towards the end of yesterday, I would like you all to focus more on the evaluation metrics of classification models, because that the rest of this phase, we will be talking about classification models. So I think a good place to start is to kind of take a step back and see which part of machine learning we're going to be looking at. So I found this neat mind map that kind of summarizes a lot of what we're going to be covering for the rest of this course. So within machine learning, we have supervised, unsupervised, and reinforcement learning. Reinforcement learning, I'll tell you all right now, we are not going to touch at all in this course. I have barely looked into reinforcement learning, but that's basically how they teach machines to play chess. That's reinforcement learning. So far what we've done is supervised learning with regression. All of our projects that we did in phase 2 were all regression projects when you're predicting some sort of continuous variable. So all of these examples that they put here, population growth, life expectancy, that's what you did, market forecasting, weather forecasting, popularity for advertising. These are all continuous variables, so these fall under regression. Now, what we're going to be talking about for the rest of this phase is classification. The only difference between the two, other than the algorithms that you use, is the target variable, instead of being continuous for this project, is going to be categorical. So just remember, our target variable for classification is going to be categorical. So I think for our project, actually, there are 4 data sets that are provided. One of them is predicting car crashes, or the outcome of a car crash. There are actually a lot of different columns in that data set that you can choose from. There is also a customer churn data set. So whether it's simply it's sort of like customer retention. That's a data set for that. And I think the data is like a telco's data. There is one that predicts the, the functionality of water wells in Tanzania. That's an interesting one. A lot of features there, whether a water well is functional or needs repair. And I think the last one is on Terry stops data, which is, it's sort of based off of stop and frisk. And it is data from Seattle, what features led to a person getting stopped. So all of these are binary or categorical outcomes, right? You either get stopped or not stopped. You get your customer churns or not churns, or retained or not retained, binary or categorical outcomes. So that's the main difference between the models that we're learning about this phase versus last phase. But however, a lot of the models that we'll be talking about this phase, even though we're talking about them in a context of classification, they actually do have regression counterparts, which we will get to. I'll mention those when we get to them. So that's under supervised learning. The other arm of machine learning is unsupervised learning. Now that's actually what we're going to hit at the very, very start of phase 4. Clustering is the example that I think is easier to understand, given you have a bunch of data. Customer or market segmentation is one of the main use cases of clustering. So let's say you have a lot of transaction data from customers, and you want to group them into 5 different groups so you can decide how to best market to these subgroups. That would be an example of clustering, and we'll hit that start of phase 4. So not to worry about supervised learning for now, but just understand that for this phase, we're mainly going to focus on classification and all the metrics and all of the strategies that come with classification modeling. Another key difference between this phase and last phase is last phase, there was a lot of focus on transforming your data, right? Looking for significant features, looking at how to, make your data more linearly related. I'll tell you that for this phase, there's a little bit less focus on that, because we'll be doing more of the work in terms of different models. So whereas last phase, we only had linear regression, this phase, we're going to have 9 different classification models that we're going to hit in the next few weeks. So just to set that expectation. And I think in our homeroom, I put the project intro. I actually moved that up. So I'll start talking about the project in week 5 out of 8. So this will be the week right before Labor Day, I think. yeah, right before Labor Day. So I'll introduce the project earlier so you all have a better idea and also more time to work on it. So excited for that. Okay, so with this overview, let's start talking about classification. And the first model that we're going to hit is logistic regression. Logistic regression is kind of like a natural yet unnatural order of models. I say that because logistic regression, very, very related to what we're doing with linear regression, but logistic regression has a lot of the assumptions that linear regression has, which, I mean, yes, it is a natural like transition into classification. However, all of our other classification models that we're going to talk about next week and onwards, we actually don't have to worry as much about like assumptions and stuff. So when it comes to the projects, logistic regression is not usually a model that students use, but we're going to talk about it anyways, because it's pretty important. Okay. So what is logistic regression? I like to think of it as just the classification counterpart to linear regression. The way that it works is extremely, extremely similar to linear regression. So to start, it belongs to a class of models called generalized linear models. And what do they have in common? They all define significant relationships between independent and dependent variables, and also they indicate the strength of the relationship. Strength by order of significance with your p-values, but also literally like the relationship itself. Coefficient, what's the magnitude of your coefficient? So again, different from linear regression, it can predict the probabilities associated with a success or a failure. So probabilities associated with a binary outcome. So is the email spam or not spam? What is the probability that the citizen will vote Republican, or Republican or Democrat, or Republican or not Republican? Binary problems. Is the homeowner going to default on their mortgage or not? If they're going to buy our product or not? Is the tumor going to be cancerous or benign? These are all scenarios where you can use for not just logistic regression, but any classification problem. What's neat about logistic regression used as a classification model is you'll see that some models this phase will strictly tell you, okay, this is class 1, class 2. Logistic regression, and we'll sort of see why that is. You kind of get a probability associated with it. So let's say you want to predict whether a tumor is cancerous or benign. You usually, from logistic regression, you can actually extract the probability that your model thinks is cancerous or benign. So that's actually something that can be pretty helpful too. But as with linear regression, logistic regression also has a set of assumptions that need to be fulfilled for your model to be consistent and reliable. So first, the dependent variable has to be binary. And I'll actually show an example where it's actually not binary, but there are 3 classes, and I'll talk about how that is happening. First, only meaningful variables should be included. So you also don't want to have, variables with high p-values. You can actually also do logistic regression through stats models, similar as how we were doing our OLS. You can pretty much get a stats models version of logistic regression as well. Next, the multicollinearity assumption also holds the same way in logistic regression as in linear regression. Next, the linearity assumption. Instead of your features just being linear related to the target, you need your independent variables to be linearly related to the log odds. Now, what log odds is, I'll talk about later, but log odds is basically a transformation, or it's a transformation of your target variable, because your target variable can only be 0 and 1. How can you get linear relationships between, for example, a continuous feature and 0 and 1? That doesn't make sense. And also logistic regression, not really an assumption, but typically does not perform well on smaller data sets. So if your data set is like under like 1,000 rows, logistic regression doesn't often perform well, but it does come down to how your data actually looks to begin with. Okay, so main differences. Again, not a linear relationship between the dependent and independent variables. However, there is that linear relationship between that and the logit model, which is basically what I was talking about, the log odds. We'll get to log odds in a little bit. The dependent variable doesn't have to be normally distributed. I mean, duh, it's just 0 or 1. You can't have that to be normally distributed either. It doesn't use OLS to do its gradient descent. So last week we talked about gradient descent and how your model decides on the best parameters using gradient descent. Now, instead of OLS, it uses MLE. And MLE, if you remember from phase 2, is basically figuring out how to best fit a curve to your data points, right? If you don't remember that, I had the example of you having a bunch of puppies and you want to figure out what the best population distribution for puppies is based on the 5 puppies that you have. That's on our playlist for those of you who weren't with us last phase. So that's MLE. So it's actually just fitting a bunch of different curves and checking to see what the likelihood is of the curve based on your data points. So it calls back that. Also, errors need to be independent but not normally distributed. So your errors, you don't really have to check for normality of your errors when it comes to logistic regression, which is good. One less thing to check for. All right, any questions at this point yet? We're about to get into like what this like logit function and like log odds thing is. Okay, awesome. So the main difference between linear regression and logistic regression is really in the target variable, right? I mean, you're doing a regression versus a classification. What's interesting about logistic regression is it's still a regression. You're just pretty much rounding off your values to 0 or 1 to get your classification. So this blue line is your typical linear model, right? Your typical linear regression equation. But when you want to have a logistic model, you are actually applying some sort of transformation to get this orange curve. Now, this orange curve, important thing about it, it is bounded by 0 and 1. So this orange curve will never get to 0. This one will never get to 1 on this side. So your values will always be between 0 and 1, which is why you always have some sort of probability associated. So whereas in a linear regression, you could say, and let me just draw something real quick. Okay, so in linear regression, let's say you have the point over here and your x value is here. And let's just say it's just one variable for now. With an x value over here, this is your regression outcome. And let's say this is, I don't know, like let's say this is 0.8. I don't know how accurate that is, but it doesn't matter. In a logistic regression, if you have your x to be over here, that goes over here, and then your probability will be 0.9. Because all of your values in a logistic regression are going to be pretty much right here and right here, it makes sense to not fit a straight line through it, instead fit this S-shaped curve. And what changes in this S-shaped curve, is kind of how steep it bends, how far apart does it stretch, like how back and forth does it go with relation to your X values, and of course in many, many dimensions as well. So this S-shaped curve is a lot more appropriate. And also when you're doing your maximum likelihood estimation, there's actually a really, really good video series on this by the StatQuest guy that I think I link at the bottom of this, because I'm not going to be able to go through all the math today. But the S-shaped curve basically, 1, aids with maximum likelihood estimation, and B, it just fits the points better. Since all of the points are like here, and like you probably will have like some outliers over here, because things are never neatly classifiable in real life, this line will make a lot more sense. So the purpose of this sigmoid transformation, you might see a few words for this transformation. You might see sigmoid, logit, or logit. I don't know how you're supposed to say it, to be honest, or log odds, all about this transformation. All right, so now that we know that this S-shaped curve is more appropriate for our data, what is the exact transformation that's going on? So, okay, so a linear to logistic transformation example kind of explain how this S-shape comes about. So let's just say that we've constructed this as our best fit line, right? Our L being this intercept plus our coefficient times value, coefficient times value, coefficient times value. Let me zoom in so it's a little clearer. Okay. So if you have this transformation where pretty much you're doing 1 plus the exponent of negative all of your coefficients, this squeezes all of your y values between 0 and 1. So it's pretty much this transformation that gets all of your values to be between 0 and 1. So therefore, what you're doing is you're choosing your best betas to fit this y instead of this straight line y. So how do you interpret this? So let's say you're trying to predict, build a model to predict whether a plant is poisonous or not. This is actually a data set that exists based on biological features of its leaves. So let's just say that 0 is non-poisonous and 1 is poisonous. Because you're forcing your predictions to be between 0 and 1, suppose for some test plant P, you get a value like 0.19. You can naturally understand this as the probability that P is poisonous, because 0 is non-poisonous, 1 is poisonous. If it's 0.19, all right, there's a 19% chance it's poisonous. So it's probably, if you set your threshold at 0.5, not poisonous. So if you want a truly binary prediction, you can round your score appropriately. So, was there a question? All good, all good. All right, so how do we fit a line to our dependent variable if it's already stored as probabilities? We can use the inverse of the sigmoid function and set our regression line to be equal to this. So the inverse of the sigmoid function, basically, how do you get from this curve back to the straight line, is given by this equation. Now, this equation is a lot simpler to read than this one over here. So then basically what you have to do is to figure out what your linear relationships will then have to be between your x variables and this. So then your linear equation, your regression equation will end up looking like this. So one way that you can go about fitting your data is training a regular multiple linear regression with this as your target. And then when you do the reverse transform, you're basically doing this transformation and you have your values like that. That's one way to go about it. However, using maximum likelihood estimation and gradient descent, they're pretty much just fitting a bunch of S-shaped curves and figuring out what's the best S-shaped curve to the data that you're given. But just to understand the relationship and that linearity relationship that is important to logistic regression, that's one way to understand it. And there's a bunch of derivations here that I don't think is important to go through at this point. All right. There's a lot of intuition here, and I understand that this is a lot. Logistic regression, honestly, if I could like teach it all, it would take maybe like at least 3 sessions. So I think I have it linked at the bottom. Yeah, I linked StatQuest's walkthrough of logistic regression, and he actually walks through how it is decided. And he walks through the MLE, the maximum likelihood estimation, like step by step, how it is fit. And so I think that's a really interesting one, especially about to understand logistic regression. Actually, before I get into that, since I just mentioned going into logistic regression, over the course of this phase, we're going to hit like 9-10 models. The expectation is not that you understand all of them fully. That's like not realistic at all. And so by the end of this phase, I'm really just going to ask that you read into 1 or 2, and that's enough. What I have put on the homeroom, I put this, where is it? A summary of all the phase 3 models on a Google Drive. And so feel free to look over here. These are all the models that we're going to hit for the rest of the phase. You're not going to get all of them. I do have like a brief write-up of each one, but I would say at the end of the phase, you're probably only going to get into like 1, maybe 2 in depth. You definitely don't have to like fully understand how every single one works, because that is just a lot. Okay. Questions at this point, since I took kind of a tangent. All right. Okay, so let's talk about implementation. Implementation for scikit-learn is extremely important, but is also extremely repetitive. So when I'm going through this coding process of coding logistic regression, you're going to see this repeating pretty much every study group from today's onwards. That's actually going to lead into a task that I'm going to give you all, which is basically to create a function that does all of these repetitive steps, which is going to feed in very, very nicely to your project, but don't worry about that for now. Okay, so the main library we're going to be using for the rest of the phase is scikit-learn. Scikit-learn, we're going to start using it for our pre-processing, as we saw yesterday. We're going to start using it for all of our modeling, and even into building pipelines. And building pipelines, I'll actually talk about that when I introduce the project, because it's really, really cool. Okay, so scikit-learn, we're importing some data sets, but we're taking our linear model from here. Pretty much it comes from the same sub library as linear regression. We're also going to normalize our data as well as perform our train test split. So we're going to load in our data, and we have our data frame over here. So this is the iris data set, which is I think it's a data set with 3 species of the iris flower with different sepal and petal length and widths. Right, so let's take a look at our target variable and how that is distributed. I would say, like with any classification problem, that's probably the first thing you want to look at. So here we can see that we have an equal number of data points in each class, which is great. So the species, I don't have the names of the species here, but species 0, 2, and 1, we have 50 points each. If we want to just plot what that looks like, if we're doing some really quick EDA, you can see that on the x-axis for each, we have the species and then also just the distribution of the values. So you can already start to see that, for example, petal width, it's kind of obvious based on like the range of values, how you might go about classifying an iris based on its petal width, right? If it's like 0 to 0.5, it's very likely to be species 0. If it's within this range, like maybe species 1, there's a little bit of overlap over here, but if it's high up, probably species 2. So based on this, you can already start to see like the separation in the classes, more in this separation later this phase. But this is just typical classification EDA. All right, so let's do our train test split pretty much the same way that we did it for linear regression. So here I set my X and Y. This is just one way to get everything except for the target. Getting my target as well. I have my train test split, and I'm going to do this same thing that I did for linear regression, fit my model on my training data and predict it on my test. So let's not worry about these hyperparameters for now. I know yesterday when we talked about ridge and lasso, we talked about hyperparameters, but no need to talk about it for now. I think the only one that would make sense first is C. C is actually the regularization parameter. So actually, let me pull that up. Logistic regression. Learn. Neat. Okay, so here you can see that C is the inverse of regularization strength, which is kind of silly because I know it's kind of not, as I was saying yesterday, it's not consistent. Like in ridge and lasso, it was alpha and now it's C. So smaller values have stronger regularization. So let's just go with the default. I think I put the default. Oh, never mind. Let's just go with 10. So a little bit of regularization. So we fit it on our train set, and we're going to predict on our test set. Cool. So let's take a look at our predictions. So this is our y-hat test, and if we did a train test split, I think this has, I don't know, 150. We have maybe roughly 30 values here, I think, if my math is right. So this is our predicted values. If we look at our actual values, if we look at our y test, it also is, let's see, 30 values here of 0, 1s, and 2s. So let's take a look at our number of values correctly predicted, which is basically which numbers match up. Like this first one, both are 2. The second one, both are 0. The last one, both are 2. I guess the second last one, the actual is 2. The predicted was a 1, so that's incorrect. So let's take a look at just how many were correctly predicted. Cool. Correctly predicted, we have 117 being true, 3 being false. And this is in our train set, sorry. In our test set, we have 28 true, 2 false. So that's a really, really quick way to see how well your model is doing, right? You want to have more correctly predicted, obviously. So right now we have 3 misclassified data points in our train set and 2 in our test set. Cool. This is not what you are going to be doing. In this next section, I'm going to show you all how to properly do your metrics, but this is just a really, really quick way to go through it. But as you can see, in implementing the models, pretty much the same thing that we did for scikit-learn and linear regression, right? Dot fit over here, dot predict, and then it's just a matter of how to use the metric that I'm going to talk about next. All of the models that we're going to talk about for the rest of the phase all follow the same series of steps: instantiate, fit, predict, and then metrics. So that's something that is going to be consistent for the rest of the phase. Neat. Okay, any questions at this point before I talk about evaluation as a whole? Okay, so evaluating classification models, before I get into all of this stuff, I want to just lay out the two main evaluation techniques that I want to see. Those are going to be confusion matrices and classification reports. I'm just going to show you all what it looks like first. So first, we have a confusion matrix, which you can get for your train set and your test set. So this is a built-in scikit-learn plotting function where you basically feed in the model, feed in your X train, Y train, and it'll plot, it'll basically throw your X train through your model automatically and spit out the values here. Now, how do you read this? I think some people find it confusing. So on this axis, you have the true label. Here you have the predicted label. What you want is everything to be across the diagonal, right? And here you can see I say normalize true. Let's actually not do that first. Normalize, let's go with false to begin. That's the, oops, is it not false? Okay, never mind. We'll get rid of this for now. Okay, so this is basically saying that 43, there are 43 data points that are actually 0 and were also predicted 0. So 43 correctly predicted as 0. Here in 37, we have 37 points that were actually 1, also predicted of 1. The 2 over here is saying that these 2 data points were actually species 1, but were wrongly predicted to be species 2. Same for this one over here. This one over here is saying that this was actually species 2, but was predicted to be species 1 incorrectly. And then this 37 is, actually 2 predicted to be 2, so that you're good. So we can see here when I do normalize equal to true, which some people like to see. I think it's kind of a personal preference. Oops. Okay, normalize equal to true basically sums it up, not sums it up, but takes it normalizes it per row. So this is just saying that out of all of the actually species 1 points, 95% of them were correctly predicted. 0.051 were incorrectly predicted as species 2, and same for here. So the values across each row will add up to 1. So that's one way to read it. So as you can see here, exactly the same thing for the test set. In the test set, we had 2 misclassified data points, and both were actually 2 wrongly predicted as 1s. So that's a confusion matrix. You're going to get used to it. I think this is a very, very useful tool to just see, like, if you have multiple classes, well, if you have more than 2 classes, what is being misclassified as 1? Cool. I know I also mentioned that logistic regression has to be binary. I'm going to talk about that later on because here we have 3 different classes. All right, but first, before that, I want to also show you a classification report, which is the other thing that I definitely want to see. So what is classification report? It basically gives you a summary of all of your scores. So this is it for the train set. This is it for the test set. And for your classification report, you're also going to get used to reading this. It gives you the breakdown of, for each class, what is the precision recall F1? And we're going to talk about precision recall F1 in a little bit, and also gives you your overall accuracy. We're going to talk about what each of those metrics are and how they differ in a little bit. But this is a really useful thing because it gives you, to some degree, it gives you a little bit more information than this does, because this kind of aggregates it for you. And the support tells you how many data points are actually in that class. So every time you're doing some sort of classification with your metrics, I always want to see your confusion matrix and your classification report for train and test for any classification model that you ever run. Cool. So now going back to what all those metrics are to begin with. We have to talk about true positives and basically true false positives and true and false negatives. So in binary classification, by default, the class 1 is positive and class 0 is negative. That's just something that is typically done in data sets. If you have multiple classes, like for example, in this data set, we had 3 classes. What logistic regression is doing is actually computing a 1 versus all approach. So instead of just doing, one logistic regression and saying like, okay, is this 0 or 1? What it's doing is kind of running 3 logistic regressions, saying like, all right, we're going to run 1 regression to say, all right, is it 0 or is it not 0? is going to run a second regression thinking that, all right, is it 1? Is it not 1? Or is it 2? Or is it not 2? So it kind of takes a 1 versus all approach. So that's how logistic regression does it for multiple classes. Why that's important is because when we're talking about true and false positives and negatives, once you have more than 2 classes, the positive and negative stop making sense, right? Because when you have like 3 species of irises, what is a positive and negative in that scenario, right? So traditionally, it was thought of in false positives, false negatives, but now, we're going to take a 1 versus all approach. Okay, but just generally, what are these metrics? The 4 metrics that are associated with classification are accuracy, recall, precision, and F1 score. So accuracy is the easiest one. Just out of all of your data points, how many were correctly predicted? So if we actually look at these numbers, we can actually infer accuracy directly. So the accuracy for this would just be whatever 117 out of 120 is, which I think is a nice number of 97.5. Yeah, all right, 97.5. This is our accuracy for this data set. And for our test accuracy is just 28 divided by 30, which is 93. So that's accuracy, very, very straightforward, correctly predicted over all of your data points. Next, you have recall. Now here you can see the equations for like true positives and like false negatives and true positive, false positives. Here's how I like to think about recall, which I think might be easier, but we'll come back to talk about this. How I like to think of recall is literally these normalized numbers over here. Recall is out of all of the out of all of the actually species 1 data points, how many were correctly predicted as species 1, right? Because how do you I like to think about it, are you recalling the correct data point? That's how I think of it. I don't know. But for recall, basically, for here, the recall is 95 for class 1, 97 for class 2, and perfect 1 for class 0. Because out of all the actual number of those data points, how many were correctly predicted? You can actually see that this corresponds with the recall over here, right? For our class 0, it was 1, 95, 97 corresponds with 95 and 97. Now, precision is just the opposite axis, right? So precision is looking at it from a row perspective. Out of all of the predicted 0, how many were actually 0? So in this case, let's use the test 1 as an example. In this case, you fully correctly predicted class 0, so you're good here. But over here, for class 1, you predicted 13 ones, but only 11 of them were actually 1s. So in this case, you can see that our precision for our test set, classes 0 and 2 have perfect precision, values of 1. And here it goes down to 0.85 because I think, 2 out of 13, 11 out of 13 should be 0.85. Yeah, 0.85, there we go. So that's how I like to think of precision and recall per class. I think especially because positive negatives don't really scale up to more than 2 classes, that's more helpful for me to think about it. So recall is just out of the actual values, how many were correctly predicted, and precision out of the predicted, how many were actually right. Different ways to think about it. F1 score though, F1 score is just a harmonic average of precision and recall. So we'll see that harmonic average is basically 2 times of the reciprocals of precision and recall, the equations over there. Okay, so let's talk about the pros and cons of each metric. The pro is it takes into account both false positives and false negatives fairly equally. A con is it can be misleadingly high when there is significant class imbalance, So class imbalance is something that is talked about in the lessons over here. Let me show you all where that is. I think it's in 25. Here we go, class imbalance problems. It's just one quick lab to show you how to deal with class imbalance problems. So imagine a scenario where here they talk about lottery ticket predictor. So let's just say your probability of winning the lottery, for simplicity's sake, is 1%. You have a 1% chance of winning the lottery. if you were to build a classification model to predict whether you will win the lottery or not, if your model always predicts that you don't win the lottery, your accuracy is still 99%, right? You still have a 99% accuracy of your model because it's always just going to predict that you're not going to win the lottery. It's going to be right 99% of the time. So that's one con of accuracy, especially if you have an imbalanced data set. And I'll talk more about the implications of imbalanced data sets during an office hour towards the end of the phase, because a couple of the data sets do have class imbalance. Okay, so to think about recall, it is highly sensitive to false negatives, no sensitivity to false positives. So if we think about that same lottery ticket prediction problem, your recall for recalling whether people will win the lottery, if your model decides to predict all don't win the lottery, is going to be 0. Because out of all the people who actually won the lottery, none of them were predicted by the model. So yeah, that's one thing about recall. For precision, precision is kind of the opposite issue. So out of all of the, I guess in this case, precision will be slightly different. How do I think about precision? Basically, if you were to look at the confusion matrix, precision and recall will worry about different things. So recall will worry more about the rows, precision will worry more about the columns. So that's one way to think about it too. Okay, so F1 score, again, the harmonic mean of recall and precision. Those are the main metrics that you're going to be using. Those are all things that you can infer from a confusion matrix as well as a classification report. Again, remember that I'm always going to want to see these in your projects. And in the function I'm going to have you build, I do expect to see all of these being returned in your function. So there is this other metric known as ROC curve, actually before that, AIC. AIC is basically very, very similar to R squared. It just talks about how well your model fits. AIC was in your linear regression output. It's just a metric of model fit, and you always prefer low AIC scores. I will say though, AIC scores not used very often, but you do see it come up once in a while. So just so you know, that's what's there. Okay. Next is ROC curve. Now, not every model supports ROC curve because it has to do with different thresholds. So not every model has thresholds involved, but ROC curve can be something that you use to look at the trade-off between your false positive and false negatives. So the math behind ROC is actually pretty intense, but the way that you read ROC, it actually is usually plotted on a graph that looks something like this. As you can see, and ROC typically comes together with AUC. AUC stands for area under curve, and ROC stands for receiver operating characteristic. So the line is the ROC curve. The area under the curve is AUC, area under curve. So you can see here, this plots your true positive rate versus your false positive rate. An ideal ROC curve fits perfectly around the top left corner. So an ideal ROC curve will look something like, oops, I'm trying to draw it, will literally look like this. This would be a perfect ROC curve, which you rarely get in practice. So as you can see here, this is a worthless ROC curve, this diagonal line over there. And as you get closer and closer to the top right edge, it gets better. So this kind of looks at your trade-off between your false positives and false negatives. So this is just another metric. I won't go into the math of it because it's pretty complicated. But for models that you can get ROC curve, basically anything that has some sort of threshold, and logistic regression is one of those things, and I'll talk about that more because I have an example later on. You can sort of see this curve, and you just have to look for a curve that goes like that. I think your lab over here goes more into detail about it if you're interested. Okay. Questions at this point about any of these metrics as a whole? I can tell you that next week's models, which are, I think it's next week's models. Let me check real quick. Next week's models both don't have ROC curve functionality. Yeah, at least definitely not the second one that we're talking about. But anyways, all right, let's talk about this in context, ROC curve in context of logistic regression. So ROC curve and AUC do come out of the scikit-learn metrics library. And one interesting thing that you have to do with ROC curves, especially if you have more than 2 classes, is think about how ROC curve plots true versus false positive rates. Again, we're dealing with this positive negative kind of scenario. So therefore, when we have 3 classes, we actually have to plot 3 curves because we kind of want to see the curve for each class for like the true versus false positive rate of each class. So that's something to think about too. So therefore, if you wanted to plot an ROC curve for a 3 or more class problem, you'll have to do a little bit of pre-processing before plotting the curve. So what we're going to do here is we're going to use a label binarizer, and I'll show you all what a label binarizer does. So it basically takes our data set, and our Y, instead of being 0, 1, and 2, is going to end up being 3 columns of dummy variables, pretty much like get dummies. Yeah, exactly like get dummies. So we've label binarized our target variable. So this helps you helps it figure out the true positive, false positive rate per class. So that's what we're doing. That we do our chain test split over here. And then you have to use the decision function. And the decision function basically gets you your it's kind of like your probability of each class per each data point. So if I show you all this right now, we're using the X test for our decision function. For each of these are associated, not exactly probabilities, but scores of each class for each data point. And that's how it's going to figure out how to plot your ROC. So this is just for a data point. This first data point will be classified as 2 because 2 has the highest score. And these scores will all add to 0, by the way. So it'll just go based on magnitude or based on, maximum value. This data point will be classified as 2. And then the second one will be classified as 0. So after all of these steps, and you have this score and this label binarized, you can print out your ROC curve. And just because you have more than 2 classes, it does make this process a little bit more difficult, which is why I'm making this plot optional for this upcoming project. But this is what it'll look like. You can see that our ROC curve, we have 1 per class. So for the first class, you have perfect prediction. You can't really see it here, but there is one that is area 1. Actually, there's 2 that have area 1 for both classes 1 and 3. And if you remember from our precision over here, because it looks at false positive rates, precision comes into play here. So precision, we have we have perfect precision for classes 0 and 2. And then this area 0.52 is for that second class. And you can see the area is only 0.52, which means that it's not very good at predicting class 2. Or this should actually be class 1, I think. Yeah. But yeah, that is ROC curve. Here are some additional resources for logistic regression. Again, only if you want to really get into the math of logistic regression. For these 2 topics, or actually really just this one topic, because I think that topic 26 is a little bit too in-depth for right now. For now, what I highly recommend focusing on is just getting used to reading these metrics, especially the confusion matrix, and understanding what all of these numbers mean in a classification report. Pretty much every topic from here on out, you're going to be working through classification problems with different models, but through all of them, you can get these metrics. So my advice is just get used to reading these metrics and thinking about, okay, for like precision of 0.97 for class 1, what does that mean? How does that correspond to my confusion matrix over here? But yeah, I know there's a lot of stuff that I covered today. I would say let it sink in, take the rest of the week and just think about classification metrics. And next week, actually, let me show you all the calendar. Next week, we'll be doing 3 study groups. So next week, we're doing 1 study group on Tuesday, one on Thursday, because Wednesday I'm doing that event. And then one actually on Saturday at our usual Saturday study group time. So make it if you can. And so because these three are just three new classification models, I think it's a good time. It's good timing because right after that, the next Tuesday, I will be introducing the project. And then that week, you'll just have 1 week where you can just like let everything sink in before we get into way more models for the last 2 weeks. So that's what the schedule is going to look like for the rest of the phase. Cool. Any questions?
Yeah, I had a question. In the beginning, it said, well, I wrote it down. Yeah, about success and failure. Is there a threshold for measuring that? Like
That's a good question. The default threshold is 50%.
Right.
So as long as it's like the probability is above or below 50%, it'll just round off to the appropriate. From logistic regression, I didn't plan on talking about this, but could be good to know. Within logistic regression, I mentioned that you can actually get the probabilities. You can actually get the probabilities here. I'm not going to walk through it now because I feel like we've already talked through a lot, but if you wanted to adjust this threshold, you could technically grab these probability estimates, set a different threshold, and then redo your classification based on these probability estimates. But by default, and there shouldn't be a reason why you want to adjust this, by default, it's 50%.
Thank you.
You're welcome. Anything else?
Quick question. What if you had an outcome that you like, kind of like saving lives or something, like what, like you're in a hospital and even though it was a false positive, like it would be like better that it did come up positive in the sense that like it's like you're catching majority of the ones that are positive, but you have some actual false positive. Is there a way to kind of adjust for that and that in logistic regression to say
that's a really I get what you mean. That's a really good question because sometimes you like as much as you can, you want to reduce either false negatives or false positives depending on context. That's extremely important to think about when you're doing your projects. And actually, as we start talking about more and more data sets with regards to classification, it's very important. And actually, I'm going to have you all do this in your projects as well to contextualize what does it mean when your model misclassifies something as like a false negative or a false positive. Because usually, and like if you're talking about like saving lives or like detecting viruses or detecting anything that's like life-threatening, usually like you definitely don't want to have any false negatives. You don't want to tell someone, oh, you don't have cancer, and then you do, you know. So in those scenarios, in context, you want to set those up. Now, in terms of optimizing for something like that, typically, for example, if let's say you had binary classification problem. Actually, let me see if there's a quick confusion matrix. Or let's see, I think there's a breast cancer data set that I can pull that from. Okay, so there's a breast cancer data set somewhere. And please have a confusion matrix here. Okay, well, this is kind of a confusion matrix. All right, so you have a confusion matrix here. Let's just say that 1 is cancerous, 0 is non-cancerous. You, as much as possible, want to reduce this number over here because you don't want to tell people that they don't have cancer when they really do. So when you're tuning your models, there will be a process where you can adjust your hyperparameters of your models to optimize for reducing this as much as possible. That I will talk about. When will I talk about this? I think I'll talk about this like sporadically throughout every model, but more so I'll do one like complete session talking about this at least before the office hours, or maybe when I talk about the project as well. Actually, yeah, when I talk about the project, that's when I'm going to introduce a method on how to do that. But yes, you can definitely optimize for a specific metric.
Okay.
Yeah, we're just not going to get to it yet. I feel like we talked about it a lot and there's a lot of material to get through. Cool. Anything else?
I just had a quick question because I mean, I went through the topic, but you said that you typically want to make 0 like the target variable and 1 the not target variable, correct? Depending on.
Okay, so for the target variable, let's say like positive versus negative, typically 1 is a positive case, 0 is a negative case. Does that make sense? So when you're talking about true, false, when you're talking about true positives, it's ones that were correctly predicted as ones. True negatives are zeros correctly predicted as zeros. False positives are ones. No, false positives are zeros predicted as ones. False negatives are ones predicted as zeros. So it's, yeah, it gets kind of confusing when you think about it in a positive negative sense because of that reason. But yeah.
No, that makes sense. I was just making sure I heard you because like it gave examples of like accuracy and stuff, but like, and when to focus on recall in the topics, I just wanted to make sure when we're like setting it up, is that something we decide for the data set or typically like that's decided for, or the context will decide it for us, I guess, more?
Yeah, I would say context will decide for it. I would say general rule of thumb, 0 is the regular case. It does depend on context actually, to be honest. So let's say like if you're detecting for cancer, usually 1 will refer to the cancerous case because you want to detect 1, which I know kind of gets confusing because like 1 then becomes positive, but having cancer is not a positive thing. Or I guess you test positive for cancer, I guess. So usually when you're trying to detect something statistically, and this is because of statistics and like how statistics has been, 1 is detecting something or a positive case.
Got it. Makes sense.
Yeah.
Ben, thank you.
You're welcome. Yeah, it's super confusing. I've had a few projects in the past where I have to tell students, okay, for reasons of like the metrics, you should just flip your zeros and ones. But when it comes to that, we will definitely talk about it. Yeah, that's one of the first things I usually talk about with students when we start talking about projects. So not to worry. Nice. Any other questions? Okay. Again, my advice is really to start honing in on the classification metrics rather than the inner workings of the models themselves. Or maybe you can just, like, I don't know, play a bunch of like the data science videos talking about the models while you focus on the metrics. Because the metrics is really what's going to drive the project, it drives the phase. And at this point, it's more important to understand how to interpret versus like how each little thing is working. So yeah, we'll eventually build up to understanding everything though. But yeah, all right. If there are no questions, I will see you all next week. Next week is going to be a busy one. We have 3 study groups, don't forget. I'll remind you all on the Slack channel as well. I keep forgetting to post in the Slack channel. But yeah, anything as usual, feel free to Slack me and let me know. Or we can talk at one-on-ones, but if there's nothing else, I will see you all next week. Great.
Thank you. Have a good night.
Bye, everybody.
All right.
Thank you. Bye.
Bye. Bye.